I welcome you once again to the third session of our integrated science class. Our previous two sessions, we've been looking at some selected practical questions under core chemistry. And all the questions we are going through have been posted on the WhatsApp page. So please, if you still haven't gotten access to the questions, you can visit the WhatsApp page and then download the questions. Yesterday, we looked at questions 3, 4, and 5. Today, we're going to continue by looking at questions 6, 7, and 8. The last question we looked at yesterday was question 5, and that was on the Molar concept, specifically preparation of standard solutions. Today we're going to look at, the first two questions we are looking at, question 6, 7, and even the question 8, that's also still under Molar concept. But specifically question 6, 7 falls under dilution. So we have application of dilution in here. Okay, so we're going to start by looking at question 6. Now question 6 reads, it says a stock solution of 1 molar HCl was prepared by dissolving 3.65 grams of HCl in 100 cm cube of distilled water. It says 5 cm cube of the stock solution was put into each of 5 measuring cylinders labeled V1, V2, V3, V4, and V5 and diluted with different amounts of distilled water to the volumes shown in the diagram below. I want you to take note of the statement 5 cm cube of the stock solution was put into each of 5 measuring cylinders. So that information is important. Okay, so from what we've read, it means that we have 1 molar solution of HCl. And the volume that was prepared was 100 cm cube. Out of this 100 cm cube of the 1 molar HCl solution, 5 cm cube was pipetted into 5 different measuring cylinders. So if you see the 5 measuring cylinders drawn in the diagram, initially the volume of HCl solution in each of them was 5 cm cube. So after pipetting the 5 cm cube of the 1 molar HCl solution into each measuring cylinder, different volume of distilled water was added to the solution in each of the measuring cylinders. The final volume arrived at, after adding the distilled water, that is what is drawn in the diagram, or that is what is indicated in the diagram. So for each measuring cylinder, the volume you are seeing there is the initial volume 5 cm cube of the solution plus the volume of water or volume of distilled water that was added. Okay. Now the actual question AI says, read and record the volumes of the solution in each of the measuring cylinders labeled V1, V2, V3, V4, and V5 respectively. So AI, we're going to look at we are looking at question 6. AI, we are recording the volumes indicated in the diagram. So V1, V2, V3, V4, and then V5. So as I've been saying, if you are supposed to read and record a value from the diagram, you are supposed to determine what each of the smaller divisions is. So if you take all the measuring cylinders, the divisions there are the same. So the first two major divisions are the 5 and the 10. So you count the number of smaller divisions between them. If you do the counting, you realize that between the 5 and the 10, we have 5 smaller divisions. So if you want what each of the smaller division is, your division will therefore be equal to 10 minus 5 over the smaller division between them, which is 5. So that will give you 5 on 5, which is 1. So the value of each of the smaller division is 1. Okay, so that should help us in reading the respective volumes. So for V1 is pointing to the first division after 5. So if each division is 1, you add the 1 to the 5, and that will be 6. So V1 is 6.0 centimeter cube. The V2 is pointing to, if you look at it very carefully, you realize that it is between the second and third division after the 5. So if each division is 1, then it means that it is pointing between 7 and 8. 7 and 8. And if you have a reading between two values, you will have to find the average of the two values. So if it is between 7 and 8, it will be 7 plus 8 divided by 2. And that will give you 7.5. So V2 is 7.5. Or let me indicate here. So you have 7.0 plus 8.0 centimeter cube divided by 2. So it's between these two divisions. So we add it and divide by 2. And that'll give you 7.5. Okay. And then you have the V3 also pointing between the values 8 and then 9. 8 and 9. So now to add the 2. So that will be 8.0 plus 9 in centimeter cube over 2. So that gives you 8.5. And then the fourth one, V4, is pointing on the 9th division. So that is 9. And then the last one is pointing on the 12. So 12.0 centimeter cube. Okay. Please kindly take note of this. If you have the meniscus curving this way, and you're supposed to read a value, for instance, from this diagram, if you go and record the value at the top, let's say the value at A, and somebody also records the value at B, you are getting two different answers. The value recorded at A is wrong. It is the one recorded at the base of the meniscus. So the value corresponding to the base of the meniscus is the correct one. So please take note of reading of volumes. If you have the meniscus curved, say that the upper part of the meniscus is pointing to a different value, and then the lower part or the base is also pointing to a different value. The correct value to record is the one pointing at the base. Okay, so please take note of that. Good. Okay, so that is that for question AI. Question AI. The II says, determine the volume of water used to dilute the 1 molar ACl in each of the measuring cylinder. If you recollect, I said that initially all the measuring cylinders contained 5 cm cube of the 1 molar ACl solution. and then distilled water was added to arrive at the volumes that we have recorded. So if you are asked to determine the volume of distilled water added during dilution, all you're supposed to do is to subtract the initial volume, that's the 5 cm cube, from the volumes you have recorded, and that will give you the volume of distilled water added. Okay, so for II, for V1, the volume of water will be equal to the V1 minus the 5 cm cube. So that will be equal to V1, which is 6 minus 5, and that will give you 1.0 cm cube. For V2, the volume of water becomes V2 minus the 5 cm cube. So, and the volume for V2 is 7.5. So you have 7.5 minus 5, and that gives you 2.5 centimeter cube. And then you have for V3, the volume of water will be V3 minus 5. Our V3 is 8.5, so 8.5 minus 5, and I'll give you 3.5. For V4, the volume of water will be V4 minus 5. Our V4 is 9. So that gives you 4 centimeter cube. And then lastly, for V5, the volume of water will be V5 minus the 5 centimeter cube. V5 is 12 minus 5, so that gives you 7. All right, so that is for how to determine the volume of distilled water that was added during dilution. You subtract the initial volume of the solution that was pipetted into each cylinder, which was 5. We subtract from the final volumes recorded, and that'll give the volume of water used during the dilution of each solution. Okay, now the B says you should calculate the concentration of the solution in measuring cylinder in V4 in I, mole per dm cube, and gram per dm cube. Sorry. Yesterday, I told you that we have two types of concentration. Concentration that has the unit molar, or mole per dm cube, is the molarity. And then the concentration with the unit gram per dm cube is the mass concentration. So if the question is asking you to find the concentration in mole per dm cube, and then in gram per dm cube, then the first one, the mole per dm cube, is the molarity. And then the gram per dm cube is the mass concentration. So indirectly, the question is asking you to find the molarity of the solution in V4, and then the mass concentration of the solution in V4. So that falls under dilution. So I'm going to put this in diagram for you to easily understand what is happening. So initially, in the measuring cylinder, I'm drawing this so that you can understand. You have a volume of 5 centimeter cube. So this is the initial solution. This contains the volume here is 5 cm cube. And then the concentration was 1 molar. Okay. So, and then when it comes to the final solution, that is what is indicated in the diagram. We are talking for V4. V4, the final volume we recorded was 9. So we have 9 cm cube. So we have the volume as 9 cm cube. The initial volume was 5. This is the final volume. This is the concentration, the initial concentration here. And then we have to find the concentration here. So since this is the initial solution, the 5 cm cube is the initial volume. The 1 molar is the initial concentration. This is the final solution. So the volume here is the final volume. We are asked to find the concentration here. So that represents the final concentration. So for I, we have initial concentration. Ci as 5 cm cube. We have initial the concentration here is 1 molar, and then the initial volume here is 1 cm cube, and then we have the final volume Vf to be 9 cm cube. Okay, so we're going to look for the concentration. That's the final concentration. How do you find the final concentration? And the initial volume is 5 cm cube here. And no, so 5 cm cube. Okay, so how do you find the final concentration? How do you find the final concentration? If you recollect, one equation we came across during dilution in theory is what we refer to as the dilution equation. And the dilution equation is given as CIVI to be equal to CF VF. So you are looking for CF. So you make CF the subject by dividing both sides by VF. And if you do that, your CF becomes CIVI over VF. Okay. So if you do the substitution, you have CF to be equal to CI, which is 1 molar, times VI, which is 5 centimeter cube, over VF, which is 9 centimeter cube. Okay, so when you punch down your calculator, that will give you 5 over 9. 5 over 9. And that will give you 5 point. Percent. that gives 0.5555. So to 3 decimal place, that will be 0.5556. The centimeter cube you can see will cancel out and be left with molar. I tell you, molar there is the same as 0 mole per dm cube. So it means the molarity of solution in V4 is equal to 0.556 mole per dm cube. Okay, so that is the BI. Please remember that in this solution, I didn't convert the volume into dm cube because both volumes are in the same unit. So as you can see, they cancelled out here. If they were in different units, for instance, one in dm cube and one in centimeter cube, then that is where you're supposed to do the conversion so that they match. Okay. Now the II, we are finding the concentration in gram per dm cube, which I said is the mass concentration. If you recollect what we did in theory, we said that the relation between the mass concentration and the molarity is giving us ρ equals C times M, where your ρ is the mass concentration and the C is the molarity, and then the M here is the molar mass. So we have determined the molarity, that's the C, of the solution in V4. So what they are supposed to do is you calculate the molar mass of the compound. The solution is made up of ACl, so you calculate the molar mass of ACl, and then the answer you get, you can use to multiply the molarity you have calculated in BI, and that will give you the mass concentration. Okay, so the first thing you do is you find the molar mass of ACl. So molar mass of ACl. The molar mass is the big M. From ACl, we have one hydrogen, and we also have one Cl. Now, if you look at the question, the value of hydrogen was giving us 1, and the Cl is giving us 35.5. If you pond that, that will give you 36.5 gram per mole. So that is the molar mass. Okay, so we can now look for the mass concentration now. So mass concentration So our mass concentration, as I said, is the C times M. But the C we are making use of is the molarity, the final molarity here. So the molarity we calculated is the CF. So you make use of the CF times the M. You don't make use of the initial concentration, that's the CI. Now, we are looking at the solution, the final solution in V4. So you make use of the molarity you have calculated, which is the final molarity, and they use to multiply the M. So that would be 0.556 times 36.5. And that will give you 20.294. The unit of mass concentration is gram per dm cube. Okay, so that gives you your answer. So anytime you're looking for mass concentration, but then you have calculated for molarity, your mass concentration will be the molarity times the molar mass. Don't forget that mass concentration is actually equal to mass over volume. Okay, so that's the formula for mass concentration. But we make use of this if you know the molarity. So once you know the value of C, you find the molar mass and then you use to multiply the molar mass. All right, so that brings us to the end of question 6. Question 6. We're going to continue by quickly looking at question 7. If you compare both questions, you realize that it is the questions are actually similar. It's just that some informations have been changed. So I don't expect anyone to have difficulties solving the question 7. But all the same, we are still going to go through it. So quickly, question 7. Okay, so question 7. Question 7. Question 7. It says that the diagrams in figure A represent volumes V equals V1, V2, V3, V4, and V5 of NaOH solutions. Each volume is obtained by adding a specific volume of distilled water to an initial volume of 5.0 cm3 of 0.1 molar or 0.1 mole per dm3 NaOH solution. So this one, to take note of the statement there, or you can underline. It says initial volume of 5.0 cm3 of 0.1 mole per dm3 NaOH solution. Okay, so it's similar to what I said in the question 6. So you have 5 measuring cylinders. You have 5 measuring cylinders, and then an initial volume of 5 cm3 of 0.1 molar sodium hydroxide solution was pipetted into each of the measuring cylinders. And then you have different amounts of distilled water added to the solutions in the measuring cylinders. And based on that, we have the final volumes after the distilled water has been added to be recorded in the diagrams indicated in the question. Okay, so question A says, determine the volume of distilled water that was added to the content of each measuring cylinder. To obtain solutions of volumes V1, V2, V3, V4, and V5. Now, so if you look at this question, in the previous question, the AI asks us to record the volume before II asks us to determine the volume of water that was used during dilution. But over here, you are being asked to determine the volume of distilled water used without first of all recording the volumes indicated in the diagram. So here, if you want to find volume of distilled water used, then it means that you have to first of all read the volume indicated in the diagram, and then you subtract the initial volume, that's the 5.0 centimeter cube, from it. Please take note of this. In the diagram in question 2, the volumes V1, V2 have not been indicated. So just like the previous one, the first measuring cylinder, on top of it, you indicate V1. The second cylinder, V2. The third, V3. The fourth, V4. And the last one, V5. Okay. So for question A, for V1, volume of water, that's VW, will be equal to V1 minus the 5.0 cm cube. So if you read the volume for V1, it's pointing, just please don't forget, as we did for question 1, you have to know the value of each of the smaller divisions. If you cross-check, between the 5 and the 10, you still have 5 divisions, 5 smaller divisions. So it will be 10 minus 5 over 5, which is still 1. Okay, so just like the question 1. So the V1 is pointing to exactly 10. So that will be 10.0 minus 5.0, giving you 5.0 cm cube. Okay, and then for V2, the volume of water will be equal to V2 minus 5.0 cm cube. From the diagram, your V2 is pointing to 12. So that's 12.0 minus 5.0. And I'll give you 7.0 centimeter cube. For V3, the volume of water will be equal to V3 minus 5.0 cm cube. From the diagram, the V3 is pointing to 15. When you subtract, that will give you 10.0. For V4, the volume of water becomes V4 minus 5.0. In the diagram, the V4 is pointing to exactly 20, so that will be 20.0 minus 5.0, giving you 15. And then the last one, for V5, the volume of water added will be V5 minus 5.0. In the diagram, your V5 is pointing to 22. So that will give you 17.0. Okay, so that is for A. A. Now the B is asking that you determine the molarity of each of the solutions of volumes V2 and V5. So here you are calculating the molarity of the solution V2, and then also you calculate the molarity of the solution in V5. Okay, so let's look at the first case for V2. Putting this in diagram, just like the previous one. You have the initial solution. Which is 5 cm cube or 5.0 cm cube. The concentration of the initial solution is 0.1 mole per dm cube. I ask you to underline that. It says initial volume of 5.0 cm cube of 0.1 mole per dm cube, Na OA solution. So the initial solution contains a volume of 5.0 and then initial concentration of 0.1 mole per dm cube. Okay, and then the final solution that is after the distilled water was added. Then we arrived at the volume. For V2, the final volume, or the value for V2 is 12. So that was the final volume. It is from this that we subtracted the initial to arrive at the volume of water that was used. So yeah, the final volume in V2 was 12. We have 12 cm cube. Okay. So yeah, we don't know the concentration, and that's what, or the molarity, that's what we have been asked to calculate. So just like we did for the first one, we have the initial volume, VI, to be 5.0 cm cube. And have the initial concentration, CI, to be 0.1. And then over here we have the final volume, to be 12.0 centimeter cube. And then we have been asked to find the final concentration. That's the CF. So we make use of the dilution equation, CI VI equals CF VF. You make CF the subject, that'll give you CI VI over VF. You substitute the values. CI is 0.1 mole per dm cube. VI is 5.0 centimeter cube. And then the VF is 12.0. Over here too, I didn't do any conversion to the volumes because they're in the same unit. Okay, if you punch that, that'll give you 0.041666 recurring. So 0.0417 mole per dm cube. If you leave it to 3 decimal place, that will give you 0.042 mole per dm cube. Okay, so yeah, molarity of solution in V2 is equal to 0.0417. Okay, so that is for V2. Remember, the question is asking to find the molarity of the solution in V2 and then V5. So this is for V2. So you go through a similar process for V5. For V5 we have the initial solution, and please don't forget that for all the measuring cylinders, the initial solution is the same. they all contain 5.0 cm cube of the 0.1 mole per dm cube NOH solution. So if you see the initial solution for V2, the information here is similar to the information for the V2. It has not changed. It's the final solution that differs. So for V5, the volume for V5 is 22. So yeah, the final volume is 22.0 centimeter cube. So we don't know the concentration, and that's what we have been asked to calculate. So we put down the information as we did for V2. So initial volume VI is equal to 5.0 centimeter cube initial concentration 0.1 mole per dm cube, and then you have the final volume VF as 22.0 centimeter cube. So we calculate for the final concentration. So still using the dilution equation, CIVI equals CF VF. On CF, CIVI over VF. CI is 0.1 mole per dm cube. VI is 5.0 cm cube. And then the VF is 22.0 centimeter cube. And when you punch, that's giving you 0.0227. So 0.0227. That's with 4 decimal places. So it implies the molarity so the molarity of solution in V5 is therefore equal to 0.0227 mole per dm cube. Okay, the last question, C. It says that calculate the amount of solid NaOH in the initial portion that was diluted to obtain the solutions. The initial calculate the amount of solid NaOH. So amount actually has to do with mole, but if you're looking at the solid NaOH, this has to do with the mass. So you are asked to determine the mass of NaOH that was diluted to obtain the solution. Diluted to obtain the solution. Okay. Now, so for C, yesterday I said that we have C calculated as N over V. Your C also calculated as mass over molar mass times volume. So here, as I said, usually if you hear the word amount of substance has to do with mole. But here, because you are looking at the amount of solid NOH that was diluted, you remember that when we are talking of preparation of standard solution, you have to weigh the substance. It is the mass that you put into the beaker and add water, and then you prepare the solution. So here, if you are talking of the amount of solid in the initial portion, it has to do with the mass. So if you are calculating for mass, say yesterday, your mass from here will be C times the molar mass times volume. You are told the initial amount, so you are using the information here. So from this initial solution, the volume is 5.0 cm cube. The concentration is 0.1 mole per dm cube. So you are left with the molar mass. So you just have to calculate the molar mass of the compound. That is why under the question, we have the values of Na given as 23, the O as 16, and then the H as 1. The H as 1. So the first thing is, you put down the information for the initial solution, where the volume or the concentration from the initial solution, C, is 0.1 mole per dm cube. The volume, V, is 5.0 centimeter cube. You are dealing with just one volume, so you convert the volume into dm cube. How do you do that? You divide it by 1,000. If you put this on a calculator, it will give you 5 times 10 to the power minus 3 dm cube. So that's the volume in dm cube. That's the same as 0.005 dm cube. Okay, so the last thing is we calculate the molar mass of the sodium hydroxide. So molar mass. The big M. We have one sodium, one Na. We have one oxygen. And I have one hydrogen. From under the question, you have the Na given as 23, the value of O given as 16, and the value of H is given as 1. When I multiply that, that'll give 40 grams per mole. So that's the molar mass. So we can now calculate for the mass of the NaOH. So using the equation C equals mass over molar mass times volume, the mass here becomes the C times the big M times the V. The C is 0.1, the molar mass 40, the volume is 5 times 10 to the power minus 3. This gives 0.2, 0.02. 0.02 grams. Bear in mind that your mass here is in grams. It's in grams. So 0.02 grams. 0.02 grams. Okay, so that brings us to the end of question 7. Question 7. We have one more question to look at. That is question 8. Question 8. Question 8. Then quick time. Stop from seeing the Okay, so the last question, question 8. Now question 8 says a stock solution of 1 molar ACl was prepared by dissolving 7.30 gram of ACl in 200 cm cube of distilled water. 5 cm cube of the stock solution was put into each of the 4 test tubes labeled C, D, E, and F. So you can underline that statement. 5 cm cube of stock solution was put into each of the 4 test tubes. And say, and diluted with distilled water to 8 cm cube, 13 cm cube, 10 cm cube, and 15 cm cube, respectively. So what does it mean? Before we continue, we have 4 different test tubes, C, D, E, and F. We have 5 cm cube of 1 molar ACl solution that was prepared. 5 cm cube of that solution was pipetted into each of the test tubes. And then different volumes of distilled water was added to arrive at the final volumes indicated in the diagram. So from 5 cm cube, the solution in D rose to a final volume of 8 cm cube. For D, the solution rose from 5 to 13. For A, it rose from 5 to 10. And then for F, the solution increased from 5 to 15. Okay. And then based on that, it says equal amount, that is W gram of zinc granules, were gently added to each of the test tubes as illustrated in the figure below. Study the figure carefully and answer the questions that follow. So after the initial volume of 5 cm cube was diluted to different volumes as indicated in the diagram, the same amount of zinc granules was put into each test tube. Okay, and based on that, you have to answer the following question. Question A says, state what would be observed in this experiment. So, from the diagram, you have an acid, ACl, in the test tube. And then you added zinc granules. Zinc is a metal. You added it to the acid. So you have a metal inside an acid. So there's going to be a reaction. So there's going to be a reaction between the metal and the acid. And whenever a metal reacts with an acid, hydrogen gas is produced. So the question is asking that what would be observed in the experiment. So during the process, a gas is going to evolve, or there will be evolution of a gas. And that gas, I said, is the hydrogen gas. And hydrogen gas is actually colorless and odorless. So the gas that will be produced, or the gas that will be coming from inside the test tube, it will be odorless. It will have no smell or no scent. It will also be colorless. It has no color. So that is observation. There will be an evolution of a colorless and odorless gas. So that is the observation. So A. In some cases, we use the word effervescence. Okay, so that is a observation that you make. There will be evolution or effervescence of a colorless and odorless gas. Sorry, this effervescence. So, evolution or effervescence of a colorless and odorless gas. Now, with time, you also realize that the amount of the zinc granules will begin to reduce. But this is actually the main observation that you see. Okay. Then BI. BI says, arrange the test tubes C, D, E, and F in order of increasing reactivity. So the question is asking that which test tube, or in which test tube would the reaction be highest? Or you are rating it from increasing means from lowest to highest. So you're going to start with the test tube in which the rate of the reaction will be slowest, up to the one that the rate of the reaction will be highest. Please bear in mind that in all the test tubes, the same amount of zinc granules was used. So it means that the only factor that is different here has to do with the concentration of the ACl solution in each of the test tubes. Originally, they all had 5 cm³ of the ACl solution, but then distilled water was added. So the more the distilled water that is added, then the lower the concentration of the ACl solution that will be arrived at. So if you look at the 4 test tubes, the final volumes indicated in the diagram for C is 8, for D is 13, for E it is 10, for F it is 15. So it means that it is C that has the lowest amount of distilled water added, followed by E, followed by D, and F has the highest amount of distilled water added. So if you are looking at the final concentrations of the solution in the 4 test tubes, that means that F will record the lowest final concentration, followed by D, followed by E, and the C will have the highest concentration. And you should have in mind that the higher the concentration, the higher the rate of what? Reaction. The higher the rate of the reaction. So since the concentration of C is the highest, the reaction in C will be the highest. And then the F is having the lowest concentration. So it will also record the lowest rate of reaction. So the question is asking us to arrange in increasing reactivity. So we're going to start from the lowest to the highest. So it means that the F will record the lowest reactivity, followed by C, followed by D, followed by E, and then C. Have in mind, whenever you're starting decreasing, as I said, decreasing from lowest to highest, you make use of the less than sign. If it is decreasing, then you start from the highest to the lowest, and that one you make use of the greater than sign. So this increasing reactivity, increasing reactivity. Okay. Now the II is asking that you give explanation for your answer in BI, and that's what I've stated already. They all contain the same amount of zinc granules, so the only factor that is different here has to do with the final concentration of the ACl solution in each of the test tubes. And the higher the concentration of the ACl solution, the higher the rate of the reaction. So the higher the concentration of the ACl solution in each test tube, the higher the rate of the reaction. So since the solution in C has the highest concentration, it will have the highest rate of reaction or the highest reactivity. And similarly, F has the lowest concentration. Okay, so the explanation is linked to the concentration of the final solution of the ACl in each test tube. If the concentration is higher, then the reactivity will also be higher. And please bear in mind that if the volume, they all have the same initial volume, but if you added more water, the one that is having more distilled water added, that means that the dilution factor is higher, and so the final concentration will be lower. So because we have a lesser amount of water added in C, that's why we are saying C is having the highest concentration. But the F has the highest amount of distilled water added, so therefore it will have the lowest concentration. Okay. Now the BII says state 3 other factors that could affect the rate of reaction in the test tubes illustrated above. So we've talked about concentration. We have several factors that affect the rate of a reaction, and one of them is concentration. So the factor we've talked about here is concentration. So the question is asking that apart from the concentration, which other 3 factors affect the rate of reaction? So we have temperature. So temperature. We also have surface area. And then you also have suitable catalysts. So you have surface area, you have temperature, surface area, catalyst. In fact, we have 5 factors that affect the rate of a reaction. You have concentration, temperature, surface area, catalyst, and then pressure. But if you remembered what we did in theory, we said that pressure only affects gaseous reactants. And this reaction involves zinc granules, which is a metal, and for that matter, solid, and ACl, which is in aqueous solution or liquid. So this do not involve gaseous reactants. So if you list pressure as one of the factors, you are wrong. So pressure will not work here because the reactants you are dealing with are not gaseous species. Okay. Question C. Question C says, name 2 other methods that can be used in this experiment. So, apart from zinc, what other method can you use? So you can make use of methods in group 1, group 2. So if you are talking group 1 methods, you have sodium, lithium, potassium. Group 2 also you have beryllium, you have magnesium, and you have calcium. So you can list any of them. So you have sodium, you can have potassium, magnesium, okay, so that is just a few. You're supposed to list just 2. And then the last question, question D. Question D says that you calculate the concentration of the solution in test tube E in gram per dm3. So this application of what we did in previous questions. Gram per dm3 means you are finding the mass concentration in E. But I told you before you can get a mass concentration, you have to find the molarity. So for E, you have your initial solution. From the preamble, it was 5 cm cube of the stock solution that was put into each of them. So you have 5 cm cube. And the concentration of the solution was 1 molar. Okay. Then the final solution. Okay, this was using test tube. So let me draw it as a test tube. The last one, the E, the final solution, the volume indicated in E is 10. So this is 10 cm cube. All right, so we have our initial volume, VI as 5. Initial concentration as 1 molar. Final volume as 10 cm cube. We look for the final concentration. And CI VI equals CF VF. So your CF VI, CI VI over VF. Our CI is 1 molar. VI is 5 cm cube. VF 10 cm cube. So that will give you 0.5 molar. Okay. So the question didn't ask you to find the molarity of the solution in E. If the question asks for molarity, then you end here. That's 0.5 molar or 0.5 mole per dm cube. But it says the concentration in gram per dm cube, which is the mass concentration. So I told you for you to find the mass concentration, which is rho, your rho is C times M. So we have calculated for the C. So we look for the molar mass and then we use to multiply. So molar mass of ACl we have 1 hydrogen and then have 1 Cl. Hydrogen is giving us 1. The chlorine, the value is also giving us 35.5. So that'll give you 36.5 gram per mole. So that's the molar mass. So you can find the mass concentration in. So mass concentration of solution in E, that's the rho. So the rho is C times M. So yeah, we are using DC, so that's CF times M. Our CF 0.5. The molar mass is 36.5. Upon that, will give you 18.25 gram per dm cube. So that's the mass concentration in the E. Mass concentration in the E. Okay. So that brings us to the end of question 8, and for that matter, the end of today's interaction. As I've been saying, if you have any challenges or problems, there's something you didn't probably understand, you can always contact me, and then I'll further explain things to you. Now, next section, we're going to look at questions and the preparation of gases. Preparation of gases. One important aspect of core chemistry practical, preparation of gases. And now, before we look at those questions, I'll be giving you some important notes. So those notes or information will be loaded onto the WhatsApp page. Please make sure you download them and go through them, read them before we meet in the next session to look at the next set of questions. Until we meet again, stay home, stay safe. God richly bless you. Bye.